Okay, welcome everyone to this week's IPLD sync meeting. It's 2020, February the 17th. And as every week, we talk about the stuff that the IPLD team is working on and has worked on and will work on the next few days. And and then discuss any open agenda items we might have. I start with myself. I've worked on the Rust IPLD stuff, and it's really getting started finally, and it's shaping up nicely. So I found the time to do some coding. So there is a PR for multi-hash, which is currently in review. And so the exciting thing is it got reviewed by quite a lot of people. So it's really by, I think, now 7 different people from 7 different companies. So it's really it's really amazing. So it's not like only PL people are reviewing, but really like independent people from other companies. So it's really nice. That is, I find it's really exciting. So this makes me really happy. And yeah, and it's shaping up quite nicely. And then the other thing is that there is currently a dev grant open for Rust IPFS, which is close to being approved. And those people already have opened an issue, which I've linked in the notes, about IPFS Rust. There's a welcome repository where we basically want to collect all the people that are involved or want to get involved with the Rust implementation of IPFS, but then also, of course, IPLD and multi-formats and so on. So in case you currently watch and want to get involved, then go to github.com/ipfsrust/welcome and find an issue there. And with those people from the dev grant, I also had a call last week, and the notes from the meeting are also linked in the notes. It was pretty good just to see what the plan is, what I need to do so they can use IPLD, what they plan to do, what the focus will be, and so on. If you're interested, just read the notes. And so what I will work on is, I did it 2 or 3 weeks ago, started with some blog API. I want to publish a draft so I can discuss those with the other people. And then also what I really need to do this week is writing a blog post about all the Rust IPFS effort, because just last week there was another repository from a company in China open that also did an Rust IPFS implementation or started. And I also pinged them that we should work together and so on. So I really want to make sure that basically get the word out so people know, where are the entry points, where get in touch with the people, and that know there's something happening, and then we can work on all the stuff together. I'm really happy this shapes up so nicely. So that's all I have. Next on my list is Tim, but he's not here. So he's working on the selector stuff. And also, it's still implementing the parser, so it's good. And I just go on to the next one, who is Rod.
Yep, it's very familiar for last week, my status. More comp stuff. So where I landed last week was, so trying to get comp generated in Lambda. We have 3 gigs. There's 3008 megs of memory and 500 megs of disk scratch to do a 1 gig piece, a comp for 1 gig piece. The best I could do is somewhere towards 3,100 megs of memory. So it just doesn't run in Lambda. And so it needs about a gig for a padded version, and then then about 2 gigs for caching during the Merkle tree calculation. Now, I think both of those pieces they could be streamlined. I think there could be a lot more. I think both of those things could be done in a streaming way, but this is deep in the bowels of the Filecoin proofs, so we're sort of stuck with that. So what I did was the Merkle tree caching backing store is pluggable. So by default, Filecoin proofs plugs in a disk backing store, and that's what we had to swap out to get it into memory with a backing store that it already ships with, which is a vector backing store. So what I did was wrote a backing store that pieced together a disk and a vector backing store, and put about just under 400 megs on disk, and then the rest in memory. And then that comes in under size in memory and uses up a bit of disk to get there. Now it's working as a Lambda. I'm actually getting results from it, at least from some simple test data for 1 gig test data. Not super confident in the code. I got Volker reviewed it for me and fixed up a bunch of my rustiness. And but there was one bug in particular there that should have been a logical bug that should have caused poor calculation, but didn't. So that raises questions about why didn't that show up as a bug in the results. So that undermines my confidence a little bit in this is doing the right thing, even though it seems to be giving me the right results. So it's the kind of thing that, as I've said before, the further we move away from using the code that, well, ideally that Lotus and Go Filecoin are using, then the more reduced confidence we should have in the results. So the more we commit to this path, the more testing we're going to have to do to make sure that our COM-P values are actually what Filecoin will be producing for the same data. So yeah, the other thing I was doing, I started fiddling with on Friday was, no, actually Saturday, writing some of this stuff in JavaScript. Not because I think that would be an ideal way to do it, but because I feel like I want more confidence in understanding what this is actually doing, because I'm making a lot of assumptions along the way. So I figure, well, just try and re-implement bits of it and see if I can get the results that I should do. And so that's an interesting exercise. Probably not going to be massively fruitful, but interesting anyway. But I should be able to. Yeah, I have a Rust Lambda that I can publish. I'm just not super confident in it. And then the other thing was I had a chat with Eric yesterday about some just general IPLD data structure, like internal representations, APIs, a little bit about the sorting stuff, key sorting, memory representation of key sorting versus codex versus all that sort of stuff. There was a minor thread on Slack. In Slack, there was a thread about this, and we had a chat about it. I took some notes. I think Eric took some probably better notes, but it occurred to us that there was the kind of stuff that really Volker should be looped in on as well while he's at the early stages of Rust implementation. Yeah, anyway, we need to get some notes out about that. That's me.
Next on my list is Michael.
Hey, yeah. So, yeah, last week I finished up a lot of like the fixes and migrations for this new slicer, for this big data project to get the car files down below a gig. Oh God, I lost like a day. I figured out that there's a segmented scan that you can do that's supposed to be faster. But the moment that I started doing it, we were then overloading our Dynamo table in terms of throughput. So I had to back off and go back to sequential. So that sucks. But nearly done sort of migrating and fixing all the basically bugs now in the old data, and clearing out all the old allocations and all that kind of stuff. And then, oh man, what else? Let me pull it up here. I had it up. Okay. Yeah, so now I have to rerun a lot of the data processing and the car part creation and all of that. And then I'll probably kind of block on the comp generation. Unless I think Rod just said that he's got it up though. We think it probably works, so we can start throwing some stuff at it. That's good.
Yeah,
because
it's at a state where you can throw stuff at it.
Okay, great. I'll pull it up and get it into Lambda. Move on from there. And even if it just works like once, I can at least get the rest of the code around it working. So that'd be good. One thing that I'm worried about is just that like it says that like the Lambda limits say that we have a 0.5 gig of temp disk. But Brian LaRue thought that was shared between the Lambda functions. So I'm gonna need to see what the deal is with that. We'll find out pretty quickly. Just run a couple of them at once. And if they crash, then we probably know why. Yeah, so that'll be interesting. So yeah, that's moving along. That'll be hopefully kind of finished up by the end of the week. All right, and then also talking with Brian, we started kicking around this idea for a database built on IPLD stuff. The best way to think of it is that it's basically a transaction log over a HAMT. So it's just like a key value store in the HAMT, and then a transaction log over all of the different manipulations on it, so that you can, like in Git, you can always kind of pull ahead and figure out what all the operations were between one point and the next, in terms of in which sequence the different operations happened on different nodes that might be manipulating the same data structure, and then you can sort of sync them around and rebase them and blah, blah, blah. So yeah, I've been poking at that a little bit, and it's made me start thinking about some of the API questions that we've had for a long time in a new light. In particular, we're definitely going to need a storage layer that knows how much of a graph is stored for a particular CID. So basically just if the whole graph is stored or not. So it's not enough to just say like, oh, I have this block or I don't. I need to know if you have everything underneath the block yet, or else I can't really do efficient sync operations. So that's one thing. Another thing is in the type generation stuff that I have from schemas, for the longest time, I had this get method on it that would get blocks out and traverse its way through multiple kind of block layers and then cast all of those into the types. And now that I'm trying to use that in this other context, I'm realizing that that's not quite the way that you want to use that. It's actually probably better to have something that takes the storage layer and takes the types and has an API for gluing them together and casting them and traversing through them properly. So I might work on that at some point as well. But yeah, that was just sort of like a nice kind of Sunday project that I started poking around at. And up next is Eric.
So I got a little more hacking done this week, but not as much as I hoped. I did not make my goal for the week of getting all of the interface changes and basic node rewrite into the core in Go IPLD Prime, or the codex traversals and stuff. That was really ambitious, turns out. What took a bit more time than I expected was primarily, while I was doing all of these new interfaces, I started, for the sake of iterating quickly, I just slung all of the new code in like one giant package and put all of the benchmarks in one package and all of this stuff, so I could just press Control-T once and that would like do it, you know? So now as I get ready to move this into the core and like make it correct and compartmentalize, taking the basic node stuff, which is what I'm renaming IPLD free. That whimsical name has finally gotten too much for me. This basic node package versus another package where I'm going to put the prototype cogen stuff that I was using to make sure that research stays on track. Pulling those out turned out non-trivial because the demo cogen stuff was using some of the internals of the basic node package. And it turns out if I want to maintain some of the contracts around immutability, these things cannot touch in such a way when they're actually in separate packages. And so there was just some learning experiences for the future of CodeGen in there. And I'm basically tabling fixing those for this package because it doesn't matter. For like it was a research project, right? So I'm just going to like kind of drop those bits. But the lesson was learned, and the good side effect is I'm getting a ton of design docs out of the week, which are probably going to continue to pay off in the future and hopefully be generalizable. I'm working on a nice little write-up of like just identifying all of the different values you could prioritize, like the speed versus the assembly size versus all these other things you could trade, and then go through the trade-off selection. And then this sort of explains a lot of the code very quickly, at least I hope. I also opened more GitHub issues than usual. If anybody listening wants to do some Golang coding work that's like pretty well defined, like self-contained, fun place to play. There's a bunch of new issues on IPLD Prime for some like traversal interfaces that I think would be cool to have and probably easy to do on top of the core stuff. So I did some write-ups on those things that I think might be good ideas, but if anybody wants to jump on them, they are now there. And I've also got one open on thinking out loud about error return strategy, because I realized some of the cases where I'm returning errors are a little verbose, and I struggle to defend the verbosity now. So anybody who has like nuanced opinions on that one, comments would be welcome. And we're maybe starting some conversations with Go IPFS about them integrating some more of all of this stuff. Those are still very early conversations, and I think research is needed on generating some concept of scope and like what would go in what order in that process. So we'll see how that goes. And that is wrapping it up for me.
Cool, thanks. I have a question for Rod about the compy stuff. So you mentioned at one point that the problem with the padding, so not the padding at the end, but what they call padding, like the bits shifting around somehow, that you can't stream it because it also goes backwards and so on. Would it be insanely complicated to change it to streaming, or is it just like insanely mildly, perhaps easy?
This is what I'm fiddling with in JavaScript right now, just to understand why. So there's this weird code in there that in Rust it needs the seek trait because it backs up. So it goes forward and then it backs up and then goes forward again. And I'm trying to understand why it backs up and why it just doesn't. Because I think it's only backing up like a byte at a time. So, you know, in theory, this is not a seek to a random place. This is just a little backing up. Yeah. So in theory, it should be really easily streamable. And why isn't this thing just caching a byte or two? Why does it need to seek? Yeah. That's what I don't understand. It's one of these pieces that it's like, what?
Okay, so basically I'm asking because like I might just like also like have a quick look at it, because like I mean basically I'm kind of like also interested in it, and it was like just like if you say okay like no way of like forget about it, I probably won't, but this sounds like I also
it is interesting code. I mean you're in the proofs, so this should be your area where it is interesting, and like the whole algorithm is interesting. It's in I'm going to paste it in the chat. It's FR32 in Filecoin proofs. There's one in storage proofs, but this one in Filecoin proofs is where most of the work is done. Where's the chat? I don't even know where the chat is anymore. There it is. It's all in there, and it's heaps of documentation. It's just some of it's really obscure. It's like, have you and I think the reason that it's really complicated is that it's allowing for arbitrary padding. So we're only caring about padding 2 bits per 254 bits. That's the padding. That's the only padding we care about. But this thing is written so that it could take any number of padding bits per bits. So it's sort of written in this hyper generic way, so it allows for these crazy edge cases. But we only care about 2 per 254. So like for that case, it should be simple, but I think it's trying to account for any arbitrary number of padding bits.
Okay. Yeah, cool. Because like this is also the file that I basically stayed away from, because like, when I ever did like some error handling improvements or logging improvements or like anything, it was like, oh no, God, oh my God, it's calling FR32. Like that's
Yeah.
So yeah, this is certainly like the one of the crazier parts of the code base. Yeah.
There's one function that's worth looking at to try and understand. It's right padded awks. So it's and it does most of the work, and it's taking that seekable stream, and it really is just it's backing up by one, and like that's all it's doing.
Okay. Yeah. Cool. Yeah. Yeah. That okay. So you answered my question. Thanks.
Yeah. Michael, I have a question for you.
Yep.
912 megs. Why that number particularly?
So one is that I wanted to keep it, so it has to be rounded to 1 meg, obviously, because a lot of the other slicing is already, like the way that we tend to slice is already aligned to 1 megabyte slices, or 1 megabyte chunks, sorry. I wanted to make sure that there was enough room for all of the blocks, all of the Unix FSV1 blocks and the car file overhead when we put a lot of small files into one of these. And we already have to keep the small car file files under a certain amount of absolute files, because then the root block gets too big. So to keep the root block under like 2 megs or a meg, it has to be something like, I think, 20,000. So yeah, the 912 is like a pretty safe number to make sure that we always have, even with all that overhead, we can keep it below the 1 meg mark.
Okay. And I thought that would, so it's mainly about the fitting the root block in the overhead pieces. Because I worked on that algorithm on the weekend to figure out what the rounding is. And it's not just up to a power of 2. It's up to a power of 2 with padding included. So the threshold would be 1016 megabytes. And as soon as you go over 1016, it would jump up to 2 gigs. So that's
interesting. Okay.
Yeah.
Interesting.
So the hard threshold for you would be 1016.
Right. But that's after all the overhead, which I can't estimate very well.
Yeah.
So I'm being a bit more conservative than I really need to be, but it's better than having, a lot of these things that are taking up like massive amounts of storage for the miners. So.
Okay.
All right.
Cool.
Anything else? I close the meeting and say goodbye to everyone, and we see us again next week. Same time, same channel. Goodbye.
Bye.